Hey guys, so we are going to be talking about atomic review. We have come to that point in our unit where it is time to wrap it all up and bring it together. So before you start this review video, you need to have tried the review questions yourself, or you should be doing them as we go along. You also need your reference table. You might want to have a calculator. You should definitely have some scrap paper to take notes on. One moment, please. Say hello, little boy. I know you can't see the camera because you can't see anything, but you gotta go. Okay? All right, we'll see how well that takes. So, let's start off at the top with question number 1. Which particle has no charge? All right, so which particle has no charge? We really only have one choice here. Electrons, those are negative. Positrons we haven't really talked about yet, but you might guess by the name they're positive. Protons are also positive, and that leaves us neutrons, which have no charge. That would be our answer. Let's look at question number 2. What is the approximate mass of a proton? So we have a couple of choices here. A is 1 unit, that stands for atomic mass unit. C is 1 gram, B is 0.0005 units, and D is 0.0005 grams. I hope that you would get rid of those gram choices right away. They're not reasonable. I'm going to switch colors here because they would definitely be too heavy for an actual proton. So the proton mass is defined as 1 atomic mass unit. It happens to be the same as the mass of an, pardon me, I'm going to go back to purple. Same as the mass of a neutron, so that would be 1 atomic mass unit or 1 unit. Question 3. What is the overall charge of an ion that has 12 protons, 10 electrons, and 14 neutrons? If we want the overall charge of that ion, notice it's ion, we know it can't be neutral, it has to have a charge that has 12 protons, 10 electrons, and 14 neutrons. So that means we have 12 positives and we have 10 negatives, and we have 14 things with no charge. We're not even going to look at those. So if we have 12 positives added to 10 negatives, that would give us a charge of 2 positive, and that puts us at choice B, being our best choice. I wanted to avoid red, but I think it's our most visible color, so I'm going to go back to that. Which phrase best describes an atom? Is it A, a negatively charged nucleus surrounded by positively charged protons, B, a negatively charged nucleus surrounded by positively charged electrons, C, a positively charged nucleus surrounded by negatively charged protons, or D, a positively charged nucleus surrounded by negatively charged electrons? Well, let's go through and do a little bit of process of elimination. Choice A, negatively charged nucleus. Let's get rid of that. We know right away that is not true. That means we can also get rid of choice B. The nucleus is always positive because it contains protons. Coming to choice C, we have a positively charged nucleus. That's right. Surrounded by negatively charged protons. Well, we know that is not true because protons are in the nucleus and they're positive, and that leaves us with choice D, a positively charged nucleus surrounded by negatively charged electrons, because electrons are negative, hanging out there out in the orbitals. Let's look at question 5. What is the number of electrons in a completely filled second shell of an atom? Is it A, 32, B, 2, C, 18, or D, 8? Well, if we remember our electron configurations, it goes 2, 8, 18, 32, and so on. And since this is asking about a completely filled second shell, that would be here with the 8. If you forget this, just go to the periodic table and look at the electron configurations within the first 3 periods. You will see it is always 2-8. We can't go higher than 8 in the second shell, and thus our best answer is D. Let's go to question 6. Which statement compares the masses of two subatomic particles? Well, they're all going to compare, but we want to know which one is correct. A, the mass of an electron is greater than the mass of a proton. B, the mass of an electron is greater than the mass of a neutron. C, the mass of a proton is greater than the mass of an electron. And D, the mass of a proton is greater than the mass of a neutron. So we know that protons have an equal mass to neutrons, and electrons are 1,836th the mass of either of those. So let's look at our choices. A cannot be the answer because it says the mass of an electron is greater than the mass of a proton. And likewise, B cannot be a correct choice because it says the mass of an electron is greater than the mass of a neutron. We know that is not true. C, the mass of a proton is greater than the mass of an electron. That is certainly possible. And D, the mass of a proton is greater than the mass of a neutron. We know that is untrue because the proton and the neutron masses are equal at exactly 1 AMU. And let's roll along to question 7. We have which statement describes the distribution of charge in an atom? All right, so where are the charges in the atom? Remember, protons are positive and they are in the nucleus. And neutrons are no charge. They are also in the nucleus. And electrons are negative and they are in the orbitals. So, A, a neutral nucleus is surrounded by one or more negatively charged electrons. B, a neutral nucleus is surrounded by one or more positively charged electrons. C, a positively charged nucleus is surrounded by one or more negatively charged electrons. Or D, a positively charged nucleus is surrounded by one or more positively charged electrons. Well, we know that protons and neutrons are in the nucleus, and protons are positive and neutrons are neutral. So our nucleus has to be positively charged, and thus we can get rid of choices A and choice B. Let's look at our last two choices then. Choice C, a positively charged nucleus is surrounded by one or more negatively charged electrons. Well, that could certainly be true because our nucleus is always going to be positive, but D also says the nucleus is positive, so let's go a little further. And we have here one or more negatively charged electrons. Yep, that is going to be our answer because if we look at choice D, it says we have positively charged electrons, and we know that is not true. We have negatively charged electrons. Let's come down to question 8. Question 8, as a result of the gold foil experiment, it was concluded that the atom, A, contains protons, neutrons, and electrons. B, contains a small, dense nucleus. C, has positrons and orbitals. Or D, is a hard, indivisible sphere. Alrighty. So, we have contains that the atom contains protons, neutrons, and electrons. Well, this is true, but that was not discovered in the gold foil experiment. Contains a small, dense nucleus. This could certainly be on the right track. Has positrons and orbitals. Well, orbitals didn't come around until the wave mechanical model, so that's out of the picture. And is a hard, indivisible sphere. Nope, that is the Dalton model. So that means D cannot be our choice. Our best choice is B, that it contains a small, dense nucleus. Remember, the gold foil experiment conducted by Ernest Rutherford proved two things about the atom. One, that there is a small, dense nucleus, and positively charged, by the way, and that the atom is mostly empty space. And on to question 8. The gold foil experiment led to the conclusion that each atom in the foil was composed mostly of empty space because most alpha particles directed at the foil, A, passed through the foil, B, remained trapped in the foil, C, were deflected by the nuclei in the gold atoms, or D, were deflected by the electrons in the gold atoms. So if we look at this is specifically asking once again about the gold foil experiment, but about the conclusion that most of the atom was empty space. So while we did have deflection of our particles, by the nuclei in the gold atoms, that did not contribute to the empty space conclusion. So we gotta get rid of that one. Our best choice there is because most passed through the foil. Because most passed through the foil, that told us that the atom was mostly empty space. While C is true, it is not the answer to this question. And we didn't have any remain trapped in the foil, and nothing is ever going to be deflected by an electron. They are too darn small. Let's go down to question 10. Which quantity represents the number of protons in an atom? A, atomic number, B, oxidation number, C, number of neutrons, or D, number of valence electrons. Now, this is one of those things you just really need to know. It is one of our facts, top 10 facts about the atom. In fact, if you ask me, and it is the fact that the number of protons in your atom is always your atomic number. That is kind of like the ID number for the element. It is how we are kind of defining those elements in terms of a number. Now, you can get to neutrons from the atomic number, etc., but it is the number of protons that is the atomic number. No ifs, ands, or buts about it. Number 11. Every chlorine atom has A, 7 electrons, B, 17 neutrons, C, a mass number of 35, or D, an atomic number of 17. Well, this is one that you definitely need the periodic table for. When you look up chlorine on the periodic table, you would see that it has an atomic number of 17, and that would be true for every single atom of chlorine, no matter what. Chlorine atoms do not have 7 electrons. They generally have 17 electrons. They do not have 17 neutrons. In fact, they have 18, but some have 17, and those would be your isotopes. A mass number of 35, well, while we kind of have a mass number of 35 here, it doesn't have to be every atom because we can have isotopes, remember? So we have isotopes that can affect, both choice B and choice C. So our best answer is choice D. What is the charge of the nucleus of an oxygen atom? Is it A, 0, B, -2, C, +8, or D, +16? So this is specifically asking about the nucleus of an oxygen atom. The answer cannot be A, because that would be the charge on a neutral atom, not a nucleus of an atom. The nucleus of the atom, remember, contains our positive protons, so the answer cannot be B because that's a negative number. So that leaves us with C and D. If you look up the atomic number of oxygen, it is 8. And remember, the atomic number is always equal to the number of protons. That gives us choice C. If somebody chooses choice D, we know that they were looking at the atomic mass or the mass number for oxygen and thinking that was the number of protons, which is never true. Your number of protons must always be smaller than your mass number, because the mass number is made up of the protons plus the neutrons. So numbers of protons must always be smaller than mass numbers. That's why you always know your atomic number is the smaller number when you compare it to the mass number. Which quantity can vary among atoms of the same element? A, mass number, B, atomic number, C, number of protons, or D, number of electrons. So they're asking which one can be different. When they say can vary, they're asking which one can be different. So we know it's not B because atomic number never changes. And because of that, we also know it's not C because number of protons also never changes, no matter what. So that leaves us mass number and number of electrons. And the word atoms is key here. While the number of electrons can vary, that only varies in ions. Vocabulary leads us to say it cannot be choice D. Our answer is choice A because once again, when mass number varies, that would be an isotope. Our question 14. An atom that has 13 protons and 15 neutrons is an isotope of what element? So let's look at our choices. Is it A, nickel, B, silicon, C, aluminum, or D, phosphorus? So we're looking for 13 protons and 15 neutrons. The neutrons part, I don't care about. It's the protons that are going to get the business done, because your number of protons is always equal to your atomic number. And your atomic number is your ID number for your element. So we go and look for atomic number 13. You need your periodic table for this. That leads us to aluminum as our one and only answer. Let's go to question 15. What is the total number of neutrons in an atom of oxygen? 18. Is it A, 18, B, 16, C, 10, or D, 8? So if we're looking for the number of neutrons in an atom of oxygen 18, remember, when we have this hyphenated form, oxygen dash 18, that 18 is the mass number. So when we look up oxygen on the periodic table, which you should have already done, oxygen has an atomic number of 8, and it has a mass of 16. So we would write, if we were doing it for the oxygen on the periodic table, it would look something like that. And our atomic number is 8. To get our number of neutrons, it is mass number minus atomic number equals neutrons. So that would be 18 minus 8 gives us 10 as our best choice. And let's go along to question 16. Question 16 gives us the following. What is the total number of neutrons in an atom of 5726 iron? Now that top number is our mass number. The bottom number is the atomic number. So to get our neutrons, we would take the mass number minus the atomic number, which would give us 57 minus 26, which would equal 31. And our best answer there is 31. It cannot be choice A because that equals the atomic number, and it can't be choice C because that equals the entire atomic mass, and choice D is just out here in case you have no idea what you're doing and you think you need to add those two numbers together. They leave that as an answer possibility for those who just have no clue. Let's go to question 17. The atomic masses and natural abundances of the two naturally occurring isotopes of lithium are shown in the table below. So we have lithium-6 with an atomic mass of 6.02 and a natural abundance of 7.5%, and lithium-7 with an atomic mass of 7.02 and a natural abundance of 92.5%. And it wants to know which numerical setup can be used to determine the atomic mass of lithium. Let's go through and see what we've got. So in choice A, we have 0.075 times 6.02. Well, that works because we know we need to move that decimal 2 spots to the left, which would give us 0.075. And we have 0.925, which is what we would get if we moved that decimal 2 spots to the left, times 7.02. So right now, that's looking like my best choice. Let's look at choice B. 0.925 times 6.02. Well, there they have crisscrossed the masses and decimal abundances, so that setup would be incorrect. On C, nothing has been converted into its decimal form, and likewise on D, they have both crisscrossed and failed to convert. So our best answer there is A. Rolling right along to question 18. An orbital is defined as a region of the most probable location of, choice A is an electron, choice B a neutron, choice C a nucleus, choice D a proton. And our best choice there is A, an electron. Electrons are found in the orbitals surrounding the nucleus. None of these other particles would possibly contain or be contained in an orbital. Let's go to question 19. Which statement describes the relative energy of the electrons in the shells of a calcium atom? A. an electron in the first shell has more energy than an electron in the second shell. B, an electron in the first shell has the same amount of energy as an electron in the second shell. C, an electron in the third shell has more energy than an electron in the second shell. Or D, an electron in the third shell has less energy than an electron in the second shell. Whew, that's a lot of combinations. Alrighty, let's break this down. If you have the nucleus, and just for the sake of simplicity, here are our shells moving away from the nucleus. Our energy increases as we move away from the nucleus. So since the energy is increasing in those electrons, as we move away from the nucleus, remember, in order to move up to an excited state, those electrons have to gain energy because their energy level has to match that in the shell that is being moved to. When they fall back down, they release that energy in the form of light. This means that as we go out, our energy levels have to increase. So we know the answer cannot be A because this says the first shell has more energy. That can't be true. B, an electron in the first shell has the same amount of energy as an electron in the second shell. Also can't be true because the energy increases as we move away from the nucleus. C, an electron in the third shell has more energy than an electron in the second shell. No. An electron in the third shell... Actually, no, wait. An electron in the third shell has more energy than an electron in the second shell. Yeah, that's going to be our answer because D, an electron in the third shell has less energy than the second shell. That can't be true. C is our best choice. 20. An electron in a sodium atom gains enough energy to move from the second shell to the third shell. The sodium ion atom becomes what? Is it A, a positive ion, B, a negative ion, C, an atom in the excited state, or D, an atom in the ground state? So let's break down our answers. A and B are both not possible choices. Ions are only formed when electrons are either completely lost or gained. And because of that, we're just moving from shell to shell within the same atom. We're not losing any electrons at all. So A and B are not possible. C, an atom in an excited state. This is definitely our best answer here because we are moving from the second to the third shell. That means we're moving higher up in our energy, and that is literally what it means to be excited. Atom in the ground state, nope, because ground state is unexcited. No electrons have gone beyond their native orbital levels. Let's look at question 21. A bromine atom in an excited state could have an electron configuration of what? So here we need to use the periodic table, find bromine, and find its electron configuration for its ground state before we really dive into these answers. So if we look up bromine, its electron configuration is 2-8-18-7. Yes, 2-8-18-7. If we go to our possibilities here, choice A, we have an electron configuration of 2-8-18-6. There, we've actually lost an electron, so that's not a possibility. C, 2-8-17-7. At first, this looks good because we have that 17, which means there's a lower level that's unfilled, but that doesn't work as well because, once again, we have lost an electron. We haven't just moved one, it's completely gone. And you know that because if you add 2 plus 8 is 10, 10 plus 17 is 27, plus another 7 gives you 34. That is not the atomic number for bromine. The atomic number for bromine is 35. Let's look at choice B, 2-8-18-7. Well, that matches the ground state, so that cannot be the answer. And choice D, we have 2-8-17-8. This is going to be the winner because we have that third shell that is not yet full, but we have electrons up there in the fourth shell. And if you do your number check, 2 plus 8 is 10, 17 plus 8 is 25. Together that gives you 35. That means we have not lost any electrons, so everything is looking good for choice D. And we want to know which elements are present in this mixture. This is a great question. So let's start off by looking at what we've got. We've got elements A, D, X, and Z here. Now remember, they're not asking you to name the actual element. These are example elements. So the choices are either A, D, X, or Z in some combination. Here we have our mixture. Now notice, they've made this question extra tough by making it so you can't actually just directly line up your lines in the spectra with the sample mixture. You have to look at the wavelengths. So here we've got a line at about 670 nanometers. So let's look and see, do we have an element that doesn't have any lines lower than 670, but has one at exactly 670? So element Z, well, that one's out because we have a line here that is smaller or higher in energy at about 705, and there's no line at 705, so we're going to get rid of that one. Element X has 2 lines at around 740, and there's no lines in the mixture at around 740, so we're going to get rid of that choice as well. Element D has 2 lines over here at about 590, and we also have those 2 lines appearing here, and that's all that element D has. And I would say those right there between the mixture and D, that makes a match. So I'm going to say D is in our mixture, and then we have our line here at 670. We have the same line in our mixture. Here we have a line at 610. We also have a line at 610 in our mixture. And just to wrap things up, here we have the line at 500 being echoed in the mixture, and the line at about 460 also being shown in the mixture. So our choices are element A and element D, which would be choice A. Question 23. In the electron cloud model of the atom, an orbital is defined as the most probable A, charge of an electron, B, conductivity of an electron, C, location of an electron, or D, mass of an electron. So once again, they are asking about orbitals, and it says the orbital is defined as what? So it doesn't even make sense to say it's the charge of an electron. Charges are positive, negative, or neutral, not orbital. Conductivity of an electron, no, that doesn't really make sense either. Mass, orbital isn't a unit of mass. Our best answer is location of the electron, and that is how an orbital is defined. Question 24. Which group of atomic models is listed in historical order from the earliest to the most recent? A, hard sphere model, wave mechanical model, electron shell model. B, hard sphere model, electron shell model, wave mechanical model. C, electron shell model, wave mechanical model, hard sphere model. D, electron shell model, hard sphere model, wave mechanical model. All right, let's break this one down. A, we know we need to start with the hard sphere model. It's the most simple model. So that means choice A or choice B are on the table because choice C and D do not start with the hard sphere model. Choice A has hard sphere model, which was Dalton's model, the first model, followed by the wave mechanical model. This would be the modern model or the most recent model, and electron shell model, which here would be the Bohr model, also known as the planetary model. Well, we know Bohr came before wave mechanical, so choice A is out the door, which leaves us with B. The correct order would be hard sphere model, electron shell, and wave mechanical. Notice they have left out the plum pudding model, which was Thomson's model, and the gold foil experiment model, or the Rutherford model, that came between the hard sphere and the electron shell. Don't forget about those. They are still around. Question 25. Compared to the energy and charge of the electrons in the first shell of a beryllium atom, the electrons in the second shell of this atom have what? Okay, your choices are A, less energy and the same charge, B, less energy and a different charge, C, more energy and the same charge, or D, more energy and a different charge. Let's start off with this basic fact. Electrons are negative. They're always negative. They're never not negative. If it's an electron, it's negative. So electrons always have the same charge. So let's get rid of choice B and choice D. Electrons will never have a different charge. So we're asking to compare the second shell to the first shell. So the second shell, would it have less energy or would it have more energy? We discussed this in a previous question. Doesn't matter what element this is, the second shell will always have more energy than the first shell. Question 26. Which atom in the ground state has the same electron configuration as a calcium ion in the ground state? Is it A, argon, B, potassium, C, magnesium, or D, neon? Okay, so here we have a calcium ion with a +2 charge. To solve this, you definitely need your periodic table. If you look at calcium, calcium's electron configuration is 2-8-8-2. If it has a +2 charge in its ion, that means we lost those last 2 electrons, which means our configuration is now 2-8-8. So, which of these elements has that same configuration? Is it argon, potassium, magnesium, or neon? The correct answer would be argon. And remember this, whenever an element is forming an ion, if it's forming its most stable form of that ion, it will attain the same electron configuration as a noble gas. And it will be the noble gas that would be formed if that ion was gaining to gain 8, to get to its octet of 8, or if it's losing to reveal the octet of 8 from underneath. Let's go to question 27, and this is a free response question. Base your answer to the following question on the information below. The element boron, a trace element in the Earth's crust, is found in foods produced from plants. Boron only has 2 naturally occurring stable isotopes, boron-10 and boron-11. It says compare the abundance of the 2 naturally occurring isotopes of boron. I'm going to give you a couple minutes to think about and answer this question. So the answer to this question regarding the most stable isotopes of boron would be that boron-11 is more abundant than boron-10. Forgive my handwriting. Boron-11 is more abundant than boron-10. And keep in mind, whenever you're asked to compare 2 things, actually reference the 2 things in your answer. Now, how do I know boron-11 is more abundant than boron-10? Well, when I look up boron on the periodic table, I see the atomic mass for boron is 10.81. Remember, your atomic mass is the weighted average of all the naturally occurring isotopes of that element. Since this atomic mass is 10.81, if I rounded that to its closest whole number value, that would round to 11, which means 11, the mass of 11 is more abundant than the boron-10 because it's contributing more to this weighted average. Question 28. Base your answer to the following question on the information below. The bright line spectra for 3 elements and a mixture of elements are shown below. Explain, in terms of both electrons and energy, how the bright line spectrum of an element is produced. So your answer needs to mention both electrons and energy. I'll give you a few minutes to come up with your answer. So on first glance, you might think this question is asking you what elements are in the mixture. And there is a second part to this question that does ask that. However, here, it's like a mini essay. We're being asked to explain, in terms of both electrons and energy, how a bright line spectrum of an element is produced. And here's the answer I would be looking for. When an electron is in ground state and absorbs energy, it goes into excited state. It can't remain in excited state, and it falls back down to ground state, emitting that energy as light. Notice I've mentioned my electrons moving from ground state to excited state, and I've mentioned that they absorb energy and then release that energy as light. This would be the complete answer that I would be looking for in this case. One thing I definitely want to mention is when you're asked to explain in terms of something on a Regents question, please make sure that you're taking the time to construct your answer to include all the things it is asking you to answer in terms of. This becomes really important because you could give an answer that's chemically correct. However, if it doesn't address the terms of the question, you wouldn't be given credit for that answer. Okay, let's go to our next question. We're going to question 29. Almost done, guys. So question 29 says copper has 2 naturally occurring isotopes. Information about the 2 isotopes is shown in the table below. We have copper 63 with an atomic mass of 62.93 AMU, an abundance of 69.17, and copper 65 with an atomic mass of 64.93 and a percent abundance of 30.83. And it says to show a numerical setup for calculating the atomic mass of copper. Take a moment and show me how you would set up that question. Okay, so here's what we're looking for. Remember, we're always going to convert our percent natural abundances into their corresponding decimal by moving the decimal 2 spaces to the left. We're going to be very careful to make sure that we are keeping the correct percent abundance with its correlating atomic mass. So we should have 62.93 times 0.6917 plus, and please show the addition that's actually happening here. If you don't include that, you can't be given credit. 64.93, which is our atomic mass for our copper 65, and I'm going to do this the right way. I left out this 0. We should always put that there. 0.3083, and this would be the correct numerical setup for calculating the average atomic mass of copper. Notice I didn't use these 2 mass numbers that were given in the names of the isotopes. If I was not given these atomic masses, it would be fine to use these masses given in the isotope names. But since I was given this more precise information, this should always be what we use in our calculation. Let's go to question 30. And 31, they both refer back to the same information. An atom in an excited state has an electron configuration of 272. It says write the electron configuration of this atom in the ground state. I'll give you a moment to do that. So we're given 272. By looking at this, we can see that the reason this is excited is because this second shell isn't full before we've put something into the third shell. So the correct ground state configuration should be 2-8-1, and that is really the only acceptable answer here. Atoms only have one possible ground state configuration. It's the excited state configurations where we can have more than one possibility. Question 31. Explain in terms of subatomic particles why this excited atom is electrically neutral. Notice again, this is an explain question in terms of subatomic particles. Okay, guys, I'm going to give you a little clue here. This is asking you to talk about subatomic particles. Really, there are 3 subatomic particles you can talk about in this answer, but not all of them may be appropriate to include. So your subatomic particles, I would say you should be thinking about should be what? So they would be your protons, neutrons. Hello, have we learned how to spell today, Miss Knoll? Oh my goodness. And your electrons. The only ones that are appropriate to include in this answer, well, it might not be all of them. Think about it. Give me an answer, and we're going to go over it in just a second. So if we want to know why this excited atom is electrically neutral, we need to think about the things that are positive and negative and how they interplay with one another. So it would make sense to include protons and electrons, but we're not going to say anything about neutrons. Now you might think that's weird because it's asking about being neutral, and neutrons are neutral, but neutrons don't actually contribute anything to this charged state of an atom, so we really need to talk about our protons and our electrons. So the way I would answer this is the atom is neutral because the number of protons and electrons are equal or are the same. So because the number of protons and the number of electrons are the same, we would have an electrically neutral atom. You could also be more detailed in your answer and say because the protons and the electrons both equal 11. You can do that. That's fine. Question 32. In the box below, draw a Lewis dot diagram for an atom of boron. Now, I know you can't really draw your boron in our Ed Puzzle answer, so explain what it should look like. So if you told me that boron should be a letter B, which is the kernel, with 2 electrons on top and 1 on the side, you would get that correct. Now remember, as far as the Regents is concerned, we can put those electrons anywhere as long as there's only 3 and there's no more than 2 on a side. However, by training you to draw them this way, when we get into our next unit, it's going to save you a world of heartache. Let's go to our last question. Base your answer to the following question on the information below. The Balmer series refers to the visible bright lines in the spectrum produced by hydrogen atoms. The color and wavelength of each line in this series are given in the table below. So it shows we have red, blue-green, blue, and violet light, all at 4 differing wavelengths. The question says, explain in terms of both subatomic particles and energy states how the Balmer series is produced. Now you might look at this and say, oh my God, Ms. Knoll, you didn't teach us anything about the Balmer series. Well, this question is designed to exploit that. It wants to confuse you, where really all it's asking is, in terms of both subatomic particles and energy, how does an atom make light? Does that help? Give me an answer and we'll come back. So, subatomic particles, if we're talking about emission spectra or light being produced from an atom, the only subatomic particle I want to be talking about are my electrons. In energy states, that would be going from ground to excited and back. So let's construct an answer. If you said that when an electron gets excited, it absorbs energy and goes into a higher energy level, then releases that energy when it returns to ground state, that's all you have to say. Or if you said light is emitted when an excited electron drops back down to ground state or down to a lower shell, that would also be completely fine. So I hope this quick journey through some review questions for our atomic topic has helped you out. If you have any questions, feel free to ask them here or bring them up in class when we see each other next time. Thanks.